Hello everybody, my name is Ajinkya Kulkarni and today I am here to discuss about fundamentals of vibrations. So this is the content of the lecture. I shall be talking about elements of system, natural frequency, time period, velocity, acceleration and displacement. The main intention of this lecture is to find out what is natural frequency and what are the parameters required to get it. So starting with the very first thing, mechanical system, that we have a spring mass system over here. This is a mass attached to this spring with stiffness K and there is a damper. So this is the classical system. Any mechanical system will have three elements. It will have mass, it will have its damping coefficient as well as it will have its stiffness. So we are going to analyze such system in which the movement is possible in only one direction. Hence it is called as 1 degree of freedom system. So and we will get it the natural frequencies of this system. So now what is meant by natural frequency? So coming to the point about natural frequency, I can tell that when a system is led into free vibration, it vibrates on its own with a particular frequency, and that frequency is called as the natural frequency. Consider a single degree of freedom like this. So this is the mass and this is the K. So this is a system. I am not talking about the damper. I shall be speaking about it in the later half of the lecture. So this is the mass, this is the stiffness. So it will have some natural frequency, okay, and the number of natural frequency in any system is equal to number of discrete masses in the system. So this is a system with one mass. Consider system with another mass like this. So here are two or three masses. This is M1 and this is M2. This is M1, this is M2. So it will have two natural frequencies. This system will have three natural frequencies and so on. So a continuous body will have infinite natural frequencies, and extracting natural frequencies from them and getting the shape desired is called as modal analysis. So that is not the topic of today's lecture. Today I shall be sticking to fundamental concept of natural frequency. So this is the agenda for today's lecture. I have drawn. So before going to this topic, I shall come to vibrations. So you must have learnt vibrations or simple harmonic motion in your physics class. So let us revise those concepts and come to the picture. So let us start. So we have a body moving in a circular motion like this. So this is a circle. So a body is moving like this, and let us say this is its diameter AB. AB is the diameter. Now this body is moving along its circle. So let us say this is the another diameter at 90 degrees. So you can see over here, this is AB diameter, which is the horizontal, and we have another diameter, let us say it is CD, COD. This is CD, diameter CD, which is perpendicular to it. Now we have taken a mass system like this one, but I am not talking about the damping in it. So I am talking about the spring and mass system. So let us draw a spring and mass system parallel to it. So how it will look? This is the you can say the surface on which the mass is going to oscillate, and this is the mass, and it is attached to this spring, and there is no damping element. Over here. So I think I have made a mistake over here. I will redraw the diagram. Just wait a minute. So these A and B are the limits of the vibration. A and B are nothing but the limits and the vibration, and the vibrating body, let us say it is starting from this angle alpha. It is called as epoch angle. So the vibrating body is starting with this alpha. So I am drawing over here like this. This is the surface, and this is the, you can see the, this is the starting point. This is the starting point. This is the mean point. Okay, and this is the end point. So these are the two extremities. I am naming it them as A dash and B dash. A dash and B dash. And I am drawing a spring over here like this, with stiffness K and mass M. Okay, so this is the diagram. I shall be getting one equation from this diagram and second one equation from the another diagram, and then I will compare those two equations to get the natural frequencies. So I am rubbing this data now. Even I can run this also, no issue in it. So I am rubbing this part like this. Let us start. So first of all, coming back to the very first diagram, this is a particle. Let us say P is a particle. It is revolving around this circle like this. It is revolving around this circle, and the radius of this circle is small a. I am writing the radius of this circle. You can see over here, this is small a, is nothing but the radius of the circle. It is performing uniform circular motion. Okay, so let omega be its angular frequency. Now what is the angular frequency? The angle covered by the object in one rotation is called as the angular frequency omega. So omega is the angular frequency. Its unit will be radian per second. Radian per second. And we have frequency f as omega upon 2 pi. So that unit will be hertz. Hertz means rotations per second. So we are having, this is another way of writing the same equation. So omega and f mean the same. So coming to over here, so this particle is revolving, particle P is revolving like around this circle in this fashion. Okay. So now what happens? Let us drop a perpendicular from this particle to this line. So that is M. Let this be capital M. So when a body is revolving around a circle like this, the foot of perpendicular from that point will perform uniform circular oscillatory motion. I am really sorry. It will perform oscillatory motion. So just you can have a look at my hands. So this is the particle and so on. Okay. So this P rotates about this circle and this M moves to and fro with O as the center point. Now similar kind of motion is seen over here. I am taking a mass. Let at point P the mass is over here. Okay, so this is the starting point of the mass. So I am now stretching the mass and releasing it. So it performs to and fro motion about the same point D, this point. So you can see over here. So this spring is getting alternately squeezed and extended, squeezed and extended. So both these motions are in short the same. circular SHM, simple harmonic motion, is nothing but the projection of circular motion on any diameter. So this is the diameter. So now let us have analytical aspect of this lecture. So now I am writing over here, this is the displacement. This is the displacement. So now the particle is this is the particle, and it is getting displayed to this position in time t. In time t. So this is alpha, and this angle is the angle covered in time t. So I can write over here like this, that it is moving with uniform circular velocity omega. It is moving with uniform circular velocity omega. Now, so come to this point, this is P dash. I drop up perpendicular to the diameter to get M dash. So M dash is nothing but the displacement, but we are calculating from the origin. So OM dash is nothing but the displacement of the particle at time t. So I am writing the same equation over here. So OM dash. Now you can see this angle is alpha, this angle is theta. So this angle will be alpha plus theta. So coming to this triangle, in triangle, I am writing over here, in triangle OP dash B. In this triangle, okay, so OM dash is nothing but the displacement, which I am writing with letter X. Okay, so OM dash is nothing but X, which is equal to, X is equal to, this is OP dash, that is the radius of the circle. So I am writing over here A sine, this is the angle alpha plus theta. Okay, then I am writing the same equation like this. X is equal to A sine, alpha will be the same as it is, but theta will be written as omega into t. So this is the expression for the displacement of the particle performing in oscillatory motion. X is equal to A sine alpha plus omega t. You can also have cosine function over here, but if you take it as a cosine function, then your diameter will not be AB, it will be CD. That's the only difference with the cosine function. But there is no harm in using the cosine term over here. Now, so this is the, you can see over here, X is equal to A sine omega t plus alpha. I am marking this equation as equation number 1. Now, derivative of displacement is velocity and derivative of velocity is acceleration. Let us do it. So I am writing over here x dot. X dot is nothing but velocity v. This is the general notation in high school mathematics, that derivatives are written over here like dots. So v is equal to x dot, and I am taking the derivative of the first equation. So it will come like this: A derivative of sine omega t plus alpha is cos omega t plus alpha into omega. So A omega cos x is equal to A omega cos, you can see over here, alpha plus omega t. I am marking this equation as equation number 2. Now I am taking derivative once again, so that will reveal the acceleration. So acceleration is equal to x double dot is equal to, and its value will be minus a omega square sine alpha plus omega t. So this is the, you can see this is the third equation. Now just have a look at the first and the third equations. So you can see we have a over here, we don't have omega square over here, but we have the term sine alpha plus omega t as it is over here. So from 1 and 3, from 1 and 3, from 1 and 3, we can get x dot double dot is equal to, x double dot is equal to minus omega square x, minus omega square x. Now let us define what do you mean by simple harmonic motion. So here in simple harmonic motion, the body is performing to and fro motion about the equilibrium point, which is called as a center or the origin. So it is performing to and fro motion about that point, such that its acceleration x double dot is directly proportional to displacement, but they two are directed oppositely. So meaning of this is that if the particle moves from the center point to the very right extremity, so its displacement will go on continuing, but its acceleration will be directed towards the center. Similarly, when it goes to this point A, acceleration is directed towards the center. So this equation is nothing but gives the meaning or definition of simple harmonic motion. So I am taking this omega square x on one side, so I get x double dot plus omega square x is equal to 0, and I am writing this as equation number 4, very important equation. So this is the first equation which we have got from this figure. So let me recap. So first we have taken the displacement of the particle, that is x, then we found its velocity x dot, and then we found its acceleration x double dot. So this is from 1 and 3, we could get that acceleration plus omega square x is equal to 0. Now since there is a constraint of space over here, I am rubbing all these equations except equation number 4, which we shall be using it later on. So I am writing this equation over here. So we got this equation as x double dot plus omega square x equal to 0, and this is equation number 4. Now coming to this diagram now. So I shall be talking about the equation for this motion. So we have mass over here. Mass is suspended with the help of a spring on a horizontal board, and then it is released. Okay, so what happens when the mass is released? It performs to and fro motion about this horizontal line. Okay, and then when it reaches its left extremity, the spring is squeezed to its maximum limit, so it has maximum potential energy at that point. It pushes the block once again, and at this point the block has the maximum velocity, and no potential energy. So this point is a point of maximum kinetic energy. So this which is pushed ahead and then it comes to the right extremity. So here also the potential energy increases, which pushes the block in the other direction. So this is the movement of the block. So we are having, this is the spring, which I am repeating once again. It gets squeezed and elongated in alternately. Now coming to the equation, let us say I am having this force, I am taking it into this direction. So it will have displacement x in this direction. Acceleration is also in this direction. So I can write it over here, mx double dot. Mx, this is acceleration and this is the restoring force. Okay, so I can write from force balance, this is mass into acceleration. This is directed over here like this. It is directed over here. But the restoring force is directed over here, which is k into x. Stiffness k into x. Okay. So I can bring this equation over here like this. So mx double dot plus kx equal to 0. Now I am dividing the equation by m. So I get x double dot plus k by m into x equal to 0. I am writing it as equation number 5. Very simple mathematics, any school boy can understand it. So now just look into the figure equations over here. X double dot plus omega square x is equal to 0 and x double dot plus k by m is into x is equal to 0. From these two equations we can compare the coefficients. So after comparing, I get this term equivalent to this term. So omega is equal to square root of k by m. So this is the natural frequency of vibration for single degree of freedom system. Omega is equal to k by m. So we could get this equation by comparing two equations, each of them obtained from different physics. So first of all we got the first equation from simple harmonic motion, and then we got from the using the equation of force balance in the spring mass system. So we could get this equation. So that was about vibration. Now coming to velocity of the vibrations and the velocity of the vibrations. I have already spoken about the displacement. So displacement was given by this OM dash. So O into M dash is equal to, this is A, radius A sine, this is theta plus omega t. Alpha plus. So this we have already discussed. This is the equation for displacement. But we also got the equation for acceleration, which is this one. But we are still left with the equation for velocity. Let us calculate it. So first of all, I am rubbing these equations. Now when I didn't rub the equations, I had received one equation like this. X dot is equal to A omega cos alpha plus omega t. This sort of equation we had already done ahead. So this is x dot is equal to A omega cos alpha plus omega t. Now I will write this cos terms in terms of sine. So this will be written in this fashion: A omega a omega 1 minus sine square alpha plus omega t. A omega into 1 minus sine square alpha plus omega t, and I will write since sine square alpha plus cos square alpha equal to 1. With this basic formula from trigonometry, I have written this equation in this form. Then I will write over here, I will take a inside. I shall take a inside, so that becomes omega into, this will be a square. When it goes inside, it will be a square. Okay, into 1 minus sine square alpha plus omega t. Alpha plus omega t. Then I will complete the bracket. Then I will write in this fashion, omega into a square minus a square into sine square alpha plus omega t is nothing but x square. So this is the expression for x dot, means velocity. This is the expression for x dot, that is velocity. So I hope you must have enjoyed the lecture. We discussed about natural frequency, then I spoke about modal analysis, then we calculated how the natural frequency can be calculated using different parameters, then we compared the equations and got the value of natural frequency. Then we found out expressions for displacement as well as the velocity of a particle performing simple harmonic motion. With this, I would like to end my lecture. Thank you.